Excellent, Chris. Thank you very much for that warm introduction. All right, standing here, I need to be here. Okay, all right, cool. And thank you, of course, to UNR and everybody here for the invitation. I think it's fantastic that local industry needs to support its institutions, and I strongly believe that, and we want to have a great relationship with UNR, which we do now, and going forward to foster cooperation between students, learning, all that kind of thing. So thank you for that. A little bit about me. I won't go back over what Chris very kindly gave that overview, but yes, I am from Australia. There's a map in case you need to get reacquainted. I did spend most of my time out here in the middle of nowhere working in the mines, and really doing chemical engineering. I was really interested in solving a lot of the environmental problems that face mining. And of course, one of the best ways to do that is actually get involved with it and learn how it's done and address the challenges that way. And after working there and all over the world in Brisbane, eventually made my way here to Reno to join Redwood Materials. And that was a very big change of pace, change of industry, but fundamentally it was still about metals extraction, metals processing, which is really my core competency. And at Redwood, leading a team of chemical engineers, technicians across all of Redwood's activities, which I'll go into talk about: recycling, refining, anode and cathode production. And really my background is in hydrometallurgical base metals processing and precious metals. And I've got a photo there. That's a photo of actually the first lithium production out of a battery recycling plant in the Western world, probably at commercial scale. So Mary Lou's there. She appears through a lot of posters I've noticed here at UNR. So really our vision is a world that's sustainably powered by a circular battery supply chain. That's really the vision that we're buying into. And when you've got a vision to align to, it really makes it easy to get out of bed every day, because this is a great vision to be working towards. And really our mission, how we're going to deliver on that vision, how we're going to action that, is we want to accelerate the reduction of fossil fuels. So we acknowledge that we can't tomorrow, go to a full electrification. We know that fossil fuels are going to be around for a while yet, but we want to accelerate that transition. And as a bit of an overview of what we do at Redwood Materials, because it is quite a lot, joining Redwood Materials, it's not just battery recycling, it's not just cathode, it's not just anode. We're trying to do everything all at once, really, really quickly, which is part of the fun. But we're doing things right at the beginning, the collection, logistics. When we get those batteries in, whether they're end-of-life EV packs, whether they're consumer end-of-life batteries, we're diagnosing and, where possible, remanufacturing. So that means getting these batteries and giving them another purpose. And then if we need to process them, then they're going through our recycling processes, where this is where the initial sorting, physical and chemical breakdowns happening. After that, refining. So really that's a removal of the impurities, separation of the metals into the streams that we want them, before finally reincorporating those back into battery materials. So in terms of delivering on our mission, here are the three things that we want to do. We want to increase the supply of battery materials, reduce the cost of batteries, and reduce the environmental impact of batteries. So here's really the story. It's a pretty familiar graph to those who are familiar with the industry, but just an exponential growth in the demand for batteries and for electric vehicles. And what really drives that is passenger EVs, and that's important because a lot of focus does need to be put on certain chemistries of batteries, high nickel batteries, LFPs. But really, this is the whole story of the demand of electrification, which starts to feed into the story of Redwood Materials. And just a huge amount of, these numbers are sort of staggering in terms of Giga Nevada today, for example, is like 35 gigawatt hours. So just a huge demand. And when we look at the specific metals, the main ones we're looking at here, they're all going to be in deficit based on that demand. So in order to meet this, conventional logic would have that more mines need to be built, more refineries need to be brought online in order to close that gap. Really, where Redwood comes in is that we develop our processes such that once these battery materials go into batteries, we can essentially recycle them indefinitely once they're into that supply chain. So the next pillar of this is to reduce the cost of batteries. So a lot of what's driving the move to electrification is policy across the major population regions in the world. And automakers are responding to this. You know, the big ones in Europe going to be 100% electric by 2030. More makers here in the States, sort of 50%. But really what it's equating to is millions of EVs that are going to be coming on the road. So this is all driven by fundamental policy coming from governments. And what we're seeing over time is the main lever that's affecting the cost of batteries. It used to be OPEX, whereas the metals were actually relatively a small part of that. And the reason for that was that we didn't have scale. And as we scale, as these gigafactories get bigger, more numerous, the skills sort of develop within here. Europe already a fair bit ahead of us in China and Japan, South Korea. This will come down, but what we're seeing, of course, is that as these demand for metals go up, the price of these metals go up. And the cost of bringing on mines, especially having worked in mining, is very significant. For example, it might take you 10 years to bring on a mine in a country like Australia that's relatively friendly to mining. In the States, obviously, a lot of you have lived that here in Nevada or other parts. It can take a very long time. So when we look further at the cost of a battery, we can actually break this down further. And really, the main parts that I want to draw your attention to is this part of the graph, which is the cost of the cathode. So this is a huge percentage of the cost. The anode is here, so the graphite, the copper foil. So this is the aluminum foil, the nickel, cobalt, aluminum, lithium. And then, of course, you've got your assembly costs. And really, as part of the cathode, you've got a huge percentage of that as the lithium, especially as the lithium price has changed over the last 5 years, and a big proportion of that coming from the nickel as well. So when it comes to the how to get at the root cause of bringing down the cost of these batteries, this is part of the graph that we want to attack. And then when you look at the total cost of an electric vehicle, you go module, pack, cell, all the way down. You're really looking at 15% of the total cost of an electric vehicle coming from the battery materials. And this is the two products that Redwood will be making. We're already making copper foil commercially out of our facility out at Sparks, and we'll also be making cathode active material as well. And it's critical that we maximise the percentage of recycled metals into those products. The third part of this is to reduce the environmental impact of batteries. This is a map really showing the flow of metals and battery materials globally. And by the time it gets to your Model Y here in the States, the metals could have travelled over 50,000 miles, and the CO2 footprint because of that is quite significant. There's also your nickel producers coming out of Russia, metals refining in China. The geopolitical complexities of these supply chains can't go unnoticed either. And really the idea here is that you've got all these metals coming from all over the world, centralised refining, largely done in China, cathode active material production in South Korea and Japan, all coming over here to the States. And really what we want to see is the circularity happening right here in the US. And this is how we're achieving it, by closing that loop right here in the US. This is a graphical representation of our Battery Materials Campus 1, which is out at Sparks, out on USA Parkway. And I'll show you an actual plot plan of a photo taken just a few weeks ago to show you the progress that we've made. But The sort of features of this, this campus that we've built part of already out at Sparks is that we have a copper foil production facility, the anode, and cathode active material production, the CAM that's put onto the aluminum foil. And as part of that, it's critical that we have recycling to feed metals into copper foil and feed metals into cathode active material production. And the recycling and refining, you can see, take up a big part of our campus. And this is still only achieving approximately 20% metals input from recycled materials. There's still a lot of metals that have to come from mining activities. So that's a bit of an overview of Redwood. That's sort of what we do. That's the mission that we're on, how we're going to achieve it. What I want to talk about now is more about our processes, our flow sheets. I'm going to talk in more detail about our recycling flow sheets, but I'm not going to really show like lots of detailed flow sheets. So please come ask after this, come and see me later. I'll be happy to answer any questions. Here's a high-level overview of Redwood's processes. So when it comes to how we integrate recycling with the manufacturing of anode copper foil, press the wrong button, sorry. Anode copper foil and cathode active material. So one of our starting materials is batteries for recycling, and that's a very generic term. But there's probably three types of batteries or battery materials that we'll take in. The first two are scraps from gigafactories. Scraps from gigafactories are very important to recyclers because that's the most stable supply of metals, and it's also the largest supply of metals at the moment. Because we don't have a lot of end-of-life EVs coming back, there's only so far drill packs and toothbrushes will take you. So production scrap from gigafactories is critical. And as we build more of these gigafactories across the US and across the world, being able to process manufacturing scrap is going to be really critical. And there's two types of manufacturing scrap. There's what we call non-live manufacturing scrap, which is primarily a battery before, at any stage of manufacturing, before electrolytes added, before any charge is added. So it could be aluminum foil with cathode active material coated onto it. It could be copper foil with graphite on it. It could be the two rolled together into what we call a jelly roll. So this non-live type of material, this would go through a mechanical processing step and a hydrometallurgical refining step to produce nickel, cobalt salts, as well as lithium salts for integration into PCAM. So that's one of our flow sheets. Non-live manufacturing scrap, mechanical processing, hydrometallurgical processing, featuring reductive sulfuric acid leaching. For live manufacturing scrap, so these are fully formed cells with a state of charge, contain electrolyte. They have a state of charge. These would be processed through a thermal processing step. Thermal processing for us is how we discharge the batteries at scale. So it's critical that we can discharge these batteries effectively for the downstream processing, but be able to do it at scale as well, because manual dismantling is very cumbersome, it's very time consuming, and it's costly, which affects the overall economics. So this is put through a thermal process. In a thermal process, this is sort of running at a moderate temperature, sort of 500 degrees Celsius, where we don't combust the graphite, and the idea here is to flash off the electrolyte. We then take that material, we call that calcined batteries. We pass that through a mechanical processing step to separate any copper foil, aluminum foil from the fine nickel cobalt graphite powders. Those oversized materials can be then split and sent to various recycling streams. The fine nickel, cobalt, graphite, lithium powder that comes out of that process is then sent through hydrometallurgical refining. So when it comes to live production scrap, we're looking at thermal processing, mechanical processing, followed by hydrometallurgical processing. And the third type of batteries that we get, which you would see a little bit of media about Redwood Materials, is really, stuff out of the junk drawers of America, drill packs, cell phones from like the 80s with heaps of gold in them. They're good. basically anything else with a battery in it, a battery with device we might call it, that would go through a sorting process, because those batteries have various different chemistries, and being able to sort your batteries as early in the process as possible. So this is sort of a principle from minerals processing and mining. The more sorting you can do up front, the better classification you can do, the better chance you have of designing a flow sheet which is going to be able to target it at that specific feed type. The more consistent you make your feed, the easier it is to design your chemical process, all those good things. So there are the first two feeds that I spoke about, the scrap from gigafactories, is predictable high grade, whereas the third type, which is really a challenge of avoiding this stuff ending up in landfills, is a lot more difficult to process. But again, this would go through a thermal processing step, followed by mechanical processing, followed by hydrometallurgical processing. Right, so that sort of covers off that couple of boxes there. What we do is, once we have those metals that are then refined in our hydromet recycling processes, the metals are presented then to precursor cathode active material production. And I'll talk about that process a little bit later, but PCAM, the precursor, and then the cathode active material production are integrated to the recycling facility. So this is really key. When we design our recycling processes, it's not going to an engineering company and saying, please give me a recycling plant. This is actually about how do we integrate the recycling flow sheet with the downstream PCAM, with the downstream CAM. When you're attempting to produce anode and copper and cathode active material at the quantities that we're looking at, this can't be met with recycling alone. So approximately 20% of the metals that will go in will be from recycled sources. Now that will vary on customer to customer. Some will be higher. Interestingly, a lot of cell phone batteries, laptop batteries are of a chemistry, a high cobalt chemistry, meaning that we can largely meet cobalt demands from recycled batteries, which is great considering where mined cobalt typically comes from, is something that we want to reduce and avoid if possible. But the balance in metals is met by what we call this sort of virgin nickel and lithium. That's mined nickel and lithium. And the mined nickel materials will still be there with us as we scale battery production, simply because we don't have the recycle units. Where we want to get to is this is supplying most of the metals, but at the moment that's not possible. So we go through precursor, mix it with a lithium, and we produce our CAM. On the copper foil, again, this can take recycled copper units. That is quite difficult to do because the copper needs to be extremely pure in order to do this. But essentially, anode manufacturing is an electrodeposition process done on continuous titanium drums, and I've got a few photos of that later. But that's sort of how the recycling processes fit into achieving these two final products. Environmental impact of recycling. Now, this is not particularly controversial because what this graph is showing is the significant reduction in environmental impact, I would say, in general, energy, CO2, water, of recycling compared to mining. And when you look at thermal processing hydromet, so that's our calcination, mechanical processing hydromet, and just our mechanical hydromet, you're sort of talking in the order of 70-80% less environmental impact. And specifically for Redwood's recycling processes, we're probably about 40% lower than typical incumbent recycling flow sheets. And a lot of that has got to do with the reagents that we use and the processing steps that we use as well. So it's not actually about thermal processes, because in our thermal processes we're not combusting the graphite. It's not about combusting separator plastic. It's actually the CO2 footprint of the reagents that you're using. And the reagents are really defined by how you set your flow sheet up. Excuse me. Oh, let me grab a bit of water. Let me talk a little bit about the copper foil production process. Excuse me. The copper foil production process is essentially an electrodeposition process. So it's like an electrowinning process, continuous electrowinning. we're taking anode recycled material, scrap copper, and scrap copper from our recycling processes as well. So the US exports in order of like 1 million tons a year of scrap copper. It's pretty crazy. There's a lot of copper available in the US, and plenty enough for us to make hundreds and hundreds of gigawatt hours of copper foil, which is great. The first thing that we do is we dissolve the copper foil through a continuous dissolving system. So there's a circulating electrolyte loop, which is about 100 gram per litre copper, 100 gram per litre acid. It's basically so it's a copper sulfate solution flowing past this big rotating drum. That drum's continually rotating, and there's a current passing through it. And basically, this is the cathode. This drum is the cathode. The anode's on the other side of the bath. And what we're doing is continually plating to remove copper out of solution, generate a small amount of acid. That acid goes back and dissolves more copper. Sorry about the recording. Basically, this stuff like rolls off the drum like a foil, but except your aluminum foil at home. This stuff's like 6 to 8 microns, so it's very, very thin. Battery grade foil. There's some surface treatment, rolling, slitting, and basically we get out of this battery grade copper foil. This is the first commercial copper foil facility in America, I think probably Europe, anywhere in the Western world really. This is actually running right now. So we're producing copper foil right now, and we're currently going through different customer qualifications. This is really what the first machine is designed to be, because in a copper foil facility you don't build sort of a gigantic version of this, you build hundreds of these machines, electrodeposition machines. So this is actually in production right now, which is really exciting. Okay, on to cathode active material. So when we're making cathode active material, it's made in primarily 2 steps. The first thing that we take is mixed sulfate metals. So this is going to be nickel, cobalt, a little bit of aluminum. And what we're trying to do is go from these nickel sulfates, cobalt sulfates, into hydroxides. And we mix the sulfates in a very specific ratio to each other. We precipitate it with sodium hydroxide, also some ammonium hydroxide as well, to produce a metal hydroxide, and that's called PCAM. The way you precipitate it is in very high-powered, high-sheared, agitated reactors. There's a very specific particle size morphology, a key to this in terms of how all the metals lock together. But this is really just your nickel, cobalt, aluminum, manganese. With the PCAM, we then pre-calcine it. This is where we start adding the lithium hydroxide. So this is where lithium is added. And then we calcine this in a number of stages, wash out, filter out the excess lithium, and then we perform some coating on the on the CAM. And this refers to coating of the particles, so that this enhances their electrochemical performance in the cells. So PCAM is really sort of a fancy precipitation with sodium hydroxide and ammonium hydroxide, and the cathode active material production is really a series of heat treatment steps. If you really wanted to break it down, my cathode colleagues would probably kill me for that explanation, but that's sort of how it's simplified. So that's how our 2 main products are made, and how recycling is integrated into making those 2 products. And this is actually our site today out at Sparks. So this is our copper foil facility. We have 1 machine running here. We're about to expand this out. This is our first hydrometallurgy refinery. So we're actually running this today. That was commissioned in June this year. So that spent a lot of time out of that plant this year. This is where we're going to be doing our first line of PCAM and CAM. So we're going to be doing this. That'll be at a stepwise sort of increment. as we bring that online. We're already running an RHK, we're already making CAM. And this is going to be our first continuous thermal processing plant. So we will continuously feed live battery materials through this kiln, this rotary calciner, which will then, the discharge of that will go through a mechanical processing, producing fractions that are suitable for hydromet refining. Down here, we'll build our next hydromet refinery. We're already starting to design that now. So this hydromet refinery here, this is the first plant of many. We're immediately going to start building another hydromet refinery here to expand our metals production capability and capacity. In the front of this hydromet plant here, there's also a mechanical processing. So the non-live manufacturing scrap would come in here. It would get prepared in a mechanical processing plant and then fed through the wall into the hydromet refinery. In terms of our battery material production plans here in northern Nevada, in terms of copper foil, we want to hit this 100 gigawatt hours per year of 6 to 8 micron copper foil. So that's battery grade. On printed circuit boards, it's typically 20 microns. This stuff's sort of 6 microns, giving you an idea of how difficult it is to make. And 100 gigawatt hours per year, it's about 35,000 tons per annum of copper. Phase 2, which is sort of more a global Redwood objective, TBD if it's to be all here in northern Nevada, but certainly 100 gigawatt hours would be where we want to end up here in Nevada. And of course, we've started production, which we actually commissioned copper foil like Christmas Eve 2022, so we're nearly coming up to a year of production now. In terms of cathode active material, we're really focusing on high nickel chemistries. So these are the typical chemistries that would go into EVs. And again, we're looking at 100 gigawatt hours per year. This is going to be a little bit later. The investment required for 100 gigawatt hours of cathode active material is significant. So this will be implemented in stages as we go. There's also a significant qualification period as well. So you can't just sort of go build one of these plants and just sort of just start selling this stuff. It'll take several years to actually qualify with, say, a Panasonic or a Toyota or an LG. But this is sort of in the order of like 60,000 tons of nickel. It's significant quantities of metal. So in terms of Redwood's locations, this is really our focus at the moment in northern Nevada. We've got a site out at Sparks. We have our site at Carson City where we have our first commercial operations. The South Carolina campus is where we're going to build our next recycling facilities. That'll be a combination of thermal processing and hydromet processing. I know for sure that's North Carolina. The rest of them sort of are in the eastern United States. That's Texas. Anyway, I did try to, I'll get better. But you can see sort of, like I was saying earlier about the gigafactory scrap is going to be so critical in terms of feeding metal tons into these recycling facilities. So this is why we're really positioned strategically here, and why Redwood sort of started out here in northern Nevada is because we're close to the only gigafactory that's running at the moment. So what can you do now? This is Redwood is quite active. You know, it's great to talk about the hundreds and thousands of tons of gigafactory scrap that'll come and sort of planning around that, but we really want to encourage people all across the country to take stuff out of their drawers, out of their homes, bring it into our collection centres so that we can actually process these and repurpose these batteries. We have nationwide drop-off locations, community collection events, direct mail-in as well, so this can all be found on our website, just as a bit of a schematic, or not a schematic, but an illustration, I suppose, of how many drop-off locations that we got across the states. So a lot of these are like Audi dealerships, and we're working with some major retailers as well for drop-off bins and stuff like that. And of course, to deliver on this mission, we are looking for lots and lots of engineers. We are currently about 750 people at Redwood now, nearly 200 engineers, and we need to get to just nearly by sort of Q1 next year, it's going to be 1,000 people as we ramp some of our operations. But we're really looking for more people, and a lot of our engineers do come from across, and scientists and technicians come from all different parts of the States, Canada, Australia, all over really. But really we want to really work as closely as we can with local institutions and getting the local workforce engaged with us as well. Great, so thank you. That's all I had. Thank you.